Assalamualaikum warahmatullahi wabarakatuh. We are from Group 4. My name is Hayaza Firasar Sabila with my last 3-digit student ID is 031.
My name is Aliana Aurelia Putri Arifa Dewi with 3 last digit student ID is 014.
And my name is Fatia Aziza with my last 3-digit student ID is 054.
In this video, we want to analyze the application of second order ordinary differential equation
and the contextual problem of harmonic motion of undamped spring. So,
let's get started!
So, in this presentation will contain the short explanation of undamped harmonic motion, the example of problems related to undamped harmonic motion, and the numerical simulation by using Maple and MATLAB. Okay, for the explanation of undamped harmonic motion, is the study of harmonic motion is fundamental in physics and engineering. One of the simplest and most illustrative example of harmonic motion is the movement of a mass attached to an ideal spring without any resistance, known as an undamped harmonic motion. This motion is governed by a second-order ordinary differential equation or ODE, which provides insight into the dynamics of the system, including its frequency, amplitude, and phase. So, in here, we explore the application of second-order ODEs in modeling the undamped harmonic motion of a spring mass system. The equation of motion, derived from Newton's second law, takes the form of a homogeneous linear differential equation. Thus, we aim to demonstrate how the second-order ODE can be used to analyze the system's parameters such as natural frequency and period. In here, we have the differential equation model. So we know that the undamped free motion system model is a system of motion with no external force, where it is Ft equals to 0 and no damping. It is T equals to 0. Hence, the differential equation model for undamped free harmonic motion system is m y double prime plus kx equals to 0. So to find the general solution, here we have the differential equation, and we divide both sides with m, so we have y double prime plus k over m x equals to 0. Then we let omega 0 is equals to square root of k over m. So we have y double prime plus omega 0 square x equals to 0. From this equation, we have the characteristic equation is lambda square plus omega 0 square equals to 0, and we have the roots of the characteristic equation is lambda 1, 2 is equals to plus minus I omega 0. Then we can form the general solution is yt equals to c1 cosine omega 0t plus c2 sinus omega 0t, or we can form it as yt equals to r cosine omega 0t minus theta, where we get it from the trigonometry identity. In here we have r is the amplitude, and r is equals to square root of c1 square plus c2 square, where the c1 is r cosine theta and c2 is equals to r sinus theta. And theta here is the phase angle, and we have omega 0 is the frequency. And if one cycle of harmonic motion that occurs is drawn in 2 pi times units, the frequency becomes f equals to omega 0 over 2 pi, and the period becomes as t equals to 1 over f, and we will get 2 pi over omega 0, or we can form it as 2 pi square root m over k.
So this is the example problem of the harmonic motion of undamped spring. Harmonic motion system of a spring depend body if the mass of the object is 1 over 4 kg and spring constant is 16 Newton per meter, the damping is 0. Then the spring when attract the object increase the length by 1 meter and starts moving upward with a velocity of 8 meter per second. No external force is applied to the system. 1. We must determine the equation model that describe the harmonic motion system of the spring in the above case. And 2. Determine the equation of motion of the object. And 3. Determine the amplitude, phase angle, frequency, and period of the motion of the object. Next, this is the solution of the problem. First, for the model equation of harmonic motion system of spring, this is the formula m times d prime y over dt prime plus k times dy over dt plus ky is equal to the function of t. Given the damping is 0, the external force is 0, the mass is 1 over 4 kg, and the spring constant is 16 Newton per meter. So that the model of the equation of harmonic motion on the spring become 1 over 4. We times it with this, and then plus 16y is equal 0. With the initial condition, initial position of the object is when y 0 is equal 1, and initial velocity of the object is dy over dt, and we substitute 0 is minus 8. And next, for the motion of the object equation, so the equation of the motion of the object is obtained by solving the differential equation model. Like this, 1 over 4 times d prime y over dt prime plus 16y is equal to 0. And then we times it by 4, and then we get this. And the solution is the characteristic of the differential equation is r, or we can say it lambda square plus 64 is equal to 0. And the roots of the characteristic equation is lambda is equal to plus minus the square root of minus 64, and then we get plus minus 8i, or imaginary. Then the general solution of the differential equation with omega 0 is equal to 8. By including the initial condition, then we get yt is equal to c1 cos 8t plus c2 sinus 8t. And next we get this by using the equation y0 or dy over dt, then we get the y prime t is minus 8c1 sinus 8t plus 8c2 cosine 8t. And then we calculate this, and then we can get the c2 is equal to minus 1. So that the equation of the motion of the object is yt is equal to cosine 8t minus sinus 8t.
Okay, so now we're gonna move on to the C problem that determine the amplitude, phase angle, and frequency, and also period by forming the equation yt cos 80 minus sin 80. Now, we have this general form of one sinus and cosinus equation of a system of motion that we have yt is equal to r cos 80 minus theta, because we have omega 0 in here is 8, and then we have r. This is the formula of r, and then we have the formula of tan is c2 over c1, and then the frequency formula in here, and then the period formula. We just substitute all of the information that has been got, that we have r in here is equal to square root of 1 plus 1 equals to square root of 2, and then for the tan theta we have minus 1 in the quadrant 4, and then we have the frequency is 4 over p, and then for the periods we have t equals to p over 4. And so we get the yt because we have r is square root of 2, and then we have theta is equal to 7p over 4. Then we can conclude that yt is equal to square root of 2 cos 80 minus 7p over 4, like that. And then for the graph, we have in the Maple version and the MATLAB version. This is the Maple graphic version, that this is the comment. And then we have, this is the output of the Maple graphic. We has the output is like this. So this is the figure of a harmonic motion figure, a harmonic motion graph. For every, in here we have a constant, what the? Because for here we have a constant motion like this. There's no damped, so this is the undamped spring. And then we have in here is the MATLAB command graphic. We have for the MATLAB, this is that we use to make a graph, and this is the output of the graph. We have same like the Maple version. The motion is always constant, not lighter or bigger like that. It's constant in every this is we got for the period of 10, yeah, 10 period like that. Okay, so we're done. So the conclusion of our presentation is studying undamped harmonic motion use second order equation helps us understand how oscillating systems work. By looking at the motion of the spring mass system, we see that how the forces create smooth back and forth movement. This approach makes it easy to figure out important details like how fast the motion is and how long it takes to complete a cycle. It also shows how these ideas can be used in real life, like in engineering and physics.
So that is the application of second order ODE in real life.
That's all from us. Thank you for watching.
Wassalamualaikum warahmatullahi